Okay, so good morning, everyone. If you haven't scanned the QR code, you can scan the QR code. Okay, so this is the last discussion. So we end up with the example of how to um, use calculus, uh, uh, finding the tangents, and then the horizontal, vertical tangent, the concavity, a little bit review of calculus 1 actually, and then sketch the curve based on all the parameters that we are find. Okay, I will continue. So after the derivative, the next thing in calculus is integration. So we need to uh, go to integration section for parametric. Let me write the name is integration. Okay, let me create some graphs. Maybe like that. Okay, maybe this is 1, and maybe this is 8. Uh, the equation is x equal, or x function t equal t squared minus 2t, and then yt t plus 1, and it will be from 1 until 4. Okay. Okay, let me mark up the -1 and 8. Uh, this -1 and 8 is from the x when we plug in 1 and 4. Okay, we plug in 1 and 4 and we get -1 and 8. And the question is, what is the area under here? Oh, let me write area. So we need to evaluate the area under the curve. Okay, this curve from -1 until 8. Okay, but actually, if you see the equations first, you need to develop the what is x, okay, from this t, and what is y from t. Okay, somehow you get this line, and actually the area is under this line, right? Okay. Now, if we look back into the calculus 1, the integral, we need to divide the area, okay, and we can, for example, this small area here, small rectangle, and we can define this as dx, okay, and this is y, right? And by evaluating this rectangle, and then we add all rectangle from -1 to 8, we can set up our integrals, right? Okay. So we can set up the, either you can uh, sub and making the y equal to plus x plus 1. Okay. So you can write also integration from -1, 8, and you can directly using the equations 2 plus and then dx. Okay. You can evaluate this if you want, but you will having maybe can you uh, turn light this light? Yeah. Okay. Good. Good. Okay. Now 2 plus squared x plus 1. Okay. Um, I think you will have difficulty here if you want to use um, some method that you have already learned, right? Uh, so I'm not suggesting to directly integrate like this if you have the parametric functions. Okay. But anyway, if you want to try, you can use some approximations. If you type in your calculator, you'll find an answer because your calculator will use some approximations like a Riemann sum, and then it will adding all, and then that's the answer in your calculator if you want. But in calculus method, aside from the approximations, it will be difficult to calculate it. So I prefer to, or I'm suggesting to just using the parametric one. Okay. So if you write the definitions, let me write the definition first. Okay. Definitions is integrations. Let's say it's a to b y dx, right? That's the definitions. Definitions of area under curve. Now, if we are breaking down these definitions, let me write this as integral y. So I will manipulate the dx. Okay. So I will write dx as dx over dt and then dt. Okay. Still similar meaning, right? Similar meaning. So to evaluate from some t1 until t2, okay, we can use y and then dx over dt, meaning the x prime, the first derivative of x, function of t, and then dt. So we can write this and add, let's say this is t1, t2. Or we can just simply write this as y x prime t and then dt. And then this is the parametric definition for integral. Or if you want to complete the equation, you can add functions of t for y, but it's still same meaning. If you want a complete form, yeah, we can write like that. Okay. I hope this making sense to you. Okay, how we can get this form. Now, looking at the questions, this x, y, and then we have some t, then we can write down integrations from 1 to 4, and then write down the yt is t plus 1, and derivative of x with respect to t is 2t minus 2, and then adding dt. And we can solve this, I think, 1, 4, and then 2t squared plus 2t minus 2t, and then minus 2. So 2t squared minus 2 dt. And we can integrate easily. And plug in 1 to 4. And we can get the number easily. Okay. Okay. Any questions first for integrations? Okay. I have this logic making sense. Okay. We just make some manipulations here. Okay. And remember that y is actually a function of t. Then we can directly plug in the endpoints from t1 to t2. Okay. Okay. So for today's class, actually, I will finish the integrations and then arc length, surface area, and then maybe a little bit introduction to polar curves. So in chapter 10, if you see the textbook, we will have the conic section. I think I will skip the whole thing, the conic section. So I will stop until the polar, and we can jump to chapter 11. Okay, and so we kind of end the chapter 10 until the polar. Okay, because the conic sections, I think you already have before, and in chapter 12 there will be some sections similar to conic sections. So I think I will just going to explain briefly the conic section in chapter 12. So the integrations. Okay, now let's move here. Now we are going to arc length. Okay, let me give you some brief or some short review. Let's just use the same or similar curve like this. And then this is -1, this is 8. And then, yeah, this is T1, this is T4. The same functions as previous, okay? Now the arc length, I hope you still remember how to find the formula. If you forget the formula, you can draw random line in graph, and then draw a tangent line in any point, and draw the triangle. So maybe here, I'll draw the tangent line. So I will mention this is dx, dy, and dl. All these three have relations in So dl is square root of dx squared plus dy squared. Okay. And with some manipulations, you can have 1 plus dy over dx or 1 plus dx over dy. Depends on the conditions of the graph, and you will have the arc length formula. Okay, from here. So I will write this in here. Okay, so arc length formula. Okay, so it's integration of dl. Let me write dl as dy over dx. Okay. Okay. So we'll write this from x1, x2 integral 1 plus or sometimes we are using L or sometimes S. Okay, sometimes S, sometimes L. This doesn't really matter. Okay, so this is the arc length formula, the general formula. Now, what is arc length in parametric? Okay, so again, we need to include the variable t. Okay, so we have the general formula, and we need to include t here. So we need to integral in terms of dt. Okay. Now arc length in parametric. Let me start with dl, like the very beginning dl here. Let me write dl as okay. Now we need to do some manipulations here. Okay. So I will divide all by dt and multiply by dt. Okay. Divide and multiply. So divide by dt, but multiply. Okay. This is also the same, dx over dt and multiply dt. Okay. Now factorize dt. Let's say this is dt squared, and we have dy over dt plus dx over dt. And simplify one more time. Or let me write the, let's say this is integral, integral. So you can see the form directly. So integral I will write dy over dt as y prime to make it simplified. So y prime t and then square and plus x prime t and square and then dt. And we can write this from t1 until t2. This is L. Okay, now we have the arc length in the parametric. Okay, so we need to include both y prime and x prime. Okay, and we need to square, and then square root, and integral all with respect to this dt. Any questions so far? Okay, I think both integral and arc length easy to follow, right? I mean, how to make sense all the formula. The key is you need to manipulate dt. Okay, so divide and multiply with dt, and you will see the form that okay, we can see the form is dy over dt here, and we already know that it's the first derivative. Okay, so the idea is to make any integrations with dt. So before you have definition with dx, right? But since okay, y and x is actually related, right? Y is function of x, but both y and x is function of t. So that's why we need to start with integral y dx to find the dt. Okay, that's the definition, okay, for parametric. So still in arc length, we also have the arc length function. I hope you still remember arc length function. So it's actually similar, but the difference is arc length functions. You are integrating the arc length from some constant to some variable. Okay, so the result will be a function. Okay, for this just arc length, the result is a number, a constant, how long the length will be. But arc length functions, the result is another function. Okay, so let me write maybe here. So arc length function. Let me write some notes. Let st. Okay, this is let st. This is arc length along the curve. Let's say the curve C. Okay, from initial point from point F A, let's say F A, G A, the XY, to a point, let's say FT, GT. Okay, so A is a constant. Okay, A is constant. A is constant. And it's still on C. On C, we can write the ST. The ST is the same arc length, but it's now we integrate from a constant to a variable t. So we can write this as integrations from a to t. And maybe we can write here. Okay, that's the arc length function. The similar thing with the our original formula. The difference is just in the integrations. Okay, this will be resulting the functions. Okay, and why I'm writing s instead of l length, because as in usually in physics, right? If you measure a distance, you have a function of distance. When you derive, you will have the velocity, right? The speed velocity, right? So the same thing, if you derive s, you will find the v, right? Velocity. And remember, to derive the integral, what you need to do is you need to use the fundamental theory of calculus. I hope you still remember. Okay. So let me write. So s t, and then let derive this d dt. This become v d, and this will be how to derive. Basically, the integral will be uh, removed, right? We will remove the integral, and we need to plug in all the informations from that endpoint. Or I can write this as prime also. So basically just this. Okay. If it's not t, let's say it's 2t. Okay. What will you write here? This is t, right? If I write 2t, what will happen here? Multiply by 2. Okay. Remember? Okay. The chain rule. Okay. If you maybe confused, go back to review your calculus one. Okay. Okay. Questions so far? Okay. Now the next one is the surface area. Okay. That's the last thing in this 10.2. So after 10.2, we will move to polar. Okay. Okay. And if we still have maybe spare time, maybe next Monday, maybe before we going through other chapters, maybe I can have some example questions from your textbook. But let's see if we still have time. Okay, that's the arc length functions. Let me move here for the surface area. Let me write the conditions. Suppose curve C is given by x function of t, y g of t, and then from alpha to some t and the endpoint, let's say beta. And then the functions all continuous, and then the y is always positive. And then the curve C traverse exactly exactly once as T increases from alpha to beta. And okay, if C is rotated about x-axis, then the area of resulting surface is, okay. Let me review what is written here. Suppose we have the curve, the functions of t, ft, and gt, t from alpha to beta. The first derivative all continues, and the functions, the y value is always positive. And then the important point is this one. Okay? The curve is traverse or moving. Okay? The curve is moving exactly once as t increases. So what does it mean? So it means it's only move like one direction, okay, only once as the t increasing. So there will be no loop. Okay. Remember that in the previous courses we can see that from the parametric we can graph looping curve, right? So to be able to calculate the surface area, we cannot really calculate the loop. Okay. So one important thing here is the curves need to be traversed exactly once. Okay. So for example, uh, okay, let's see this is the curve. Okay. You need to rotate about the x-axis. So when you rotate here, you can evaluate, right? So based on what we have done in calculus 1, the resulting surface is, let's say, S equal integral of 2 pi y, and then let's say ds, or dl if you want to make it consistent. Okay, so if you rotate about the x, it will be 2 pi y. If you rotate here, it will be 2 pi x. Okay, and now because we also already defined the dl in arc length, right? In parametric, we can go to the parametric formula. So basically, the surface area uh, is depends on what we have calculated in arc length. Okay, so we can go here 2 pi y, and then write down the square root of, and because now we are evaluating the dt, this is alpha and beta, as we define alpha beta as t, from t1 to t2 or alpha beta. Okay. And same thing if you have rotations about y, so 2 pi x. Okay. Maybe I'll give you one example, maybe the surface for surface area, and then we can move to polar curves. Any questions first for the surface area? Okay. I think as long as you understand the arc length, the surface area is not too complicated. What you need to remember is rotating about x and rotating about y. Okay? If you rotate about x, this is 2 pi y. Rotate about y will be 2 pi x. Do you know how we define y and x? This is actually the radius. Okay, so this radius is y, right? And this radius, if you rotate here, is the x. Okay. If you maybe want to review, you can check your calculus one. Okay. Okay. Let me give you the questions. Find the area of surface obtained by rotating the given curve about x-axis. So x, let me give you another functions. Let's say this x is t cubed and y is t squared. And from 0 to 1. Okay. I think what you need to do is just using the previous formula. And it's I need to remind you on how to integrate the arc length, the surface area. Okay. So basically, what you need to do is just using the previous formula, and then calculate using the integrations. Okay. Calculation the integrations. Any integration technique you know or you remember, you can use that also. So if the formula, okay, I can write the formula as from 0 to 1, and then 2 pi y, and then let's just write the dl. Or if you want to write the dl as long formula, it's also fine. Um, the number is it's not a simple number, I think. But uh, um, if you find any questions, maybe in the exam or my quizzes, usually I will prepare a simple calculations, okay, for the number. But if somehow you find that, you can find or you can work the questions until the um, before the calculation ended. That you can stop there because the point will be the same with the if you find the exact number, I will give the same point because that is not important in calculus. Okay, we can derive the x and y. And then maybe square this. and then plus this, right? So 9, 3, 4. And we can write the S. We can, okay. So S is 2 pi, what is Y? It's t squared. So 2 pi t squared, and then a square root of t squared 9t squared plus 4, and then dt. Okay, any idea how to solve this? Okay, okay. Okay. Any idea? Under idea? Hmm. Anyone find? This is just warming up all your memories. Any idea? Any? No? Okay. Have you tried this? Okay. You fine? No? Why? Okay. 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 Is it? You got it? Are you sure? It's yeah. Okay. Okay. Uh, what I want to show you is we can use just simple substitutions. If I write u, let me find this 90 squared. Okay. If I derive this, we can get 18t, right? And from here also, we can find t squared, okay, is u minus 4 divided by 9. Okay. Forgot here, tdt. And tdt is 1 over 18 du. Okay. So based on all these informations, and also we can set up when t is 0, u is 4, and when t is 1, u is 9 plus 4 is 13, right? And we can set up a new endpoint from 4 to 13. So 2 pi, or let me write 2 pi outside. 2 pi, so u minus 4, 9, and then square root of, or okay. So tdt is from t squared dtt going outside. So tdt, I will substitute with this directly. And square root of 9t squared plus 4 is square root of u. Okay. So we can simplify 9, 18. Let me move here. Still have 4. And I will multiply u minus 4 with 6 squared of u. Okay. So we will have u 1 plus half is 3 over 2 minus 4 u half. And now this will be pi over 81, and u 5 over 2 minus um, 3 over 2, 2 over 3, 2 over 3, 8 over 3, right? And plug in 4 and 13. Okay. If you stop here, if you get some questions like this in the exam, you stop here, you get full point. Okay, no need to going further. It's waste of time. Okay. You already done the calculus part here, and it's okay. It's fine. This is already full point for me. Okay. Unless I give you A, B, C, then there's some number there. You need to check the number. Okay. If you want, you can go and find the number, but my suggestion is stop here. Okay. Okay. Now, any questions? Sometimes the integrations you can use many techniques. Okay. You can use this. The simple one is the substitutions. Okay. And then the by parts. Okay. So most cases, if you feel you can substitute something in the equations and make it easy to integrate, then use that first. Okay. If not, use the by parts, or substitute with trigonometric. Okay. If you see any any equations that uh, you feel easier to substitute. Okay. Now we will move to 10.3, which is the polar coordinate system. I will move to the new page. Um, so what is polar coordinate system? Okay. So polar coordinate system. Okay. Uh, Before you learn that you have axis like this, and you name this is y and this is x, right? This is, we say sometimes the Cartesian, or sometimes we say rectangular. Why we say rectangular? Because we can make a coordinate like a rectangle, right? So maybe if I make a point here, let's say this is x1, y1, or maybe point here, x2, y2. Okay. So if we are looking at the paper, or maybe you can imagine like a grid, a paper with grid. Grid is like this. So sometimes you easy to making graph. Okay, maybe when you are junior high, you are told by your teacher, okay, we can please make graph with this grid paper. Or if you experience this, no, paper with grid blocks, no. Okay, anyway, yeah, I've experienced before, and I remember. Okay, this is why it is called rectangular, because you can see the rectangle, right? X1. Okay. Now in 10.3, we will move away from here. Okay, we are moving away. We move away to a polar system. So polar system, it's based from, we call this a polar axis. So it's based off the based on the circular movement. So let's say this is the base, and how you move is counterclockwise. Okay. So let me make some line here. Let me move to the right side. And let's say we have the angle theta. And let's say we have this P. And how we define our point here is not by X or Y. This is radius and theta. Okay. So radius and theta. And you need to start always from the baseline here. So when you move, maybe, oh, pi over 3, or maybe pi over 2. So you say, maybe the r is 1, 1, and then pi over 2, meaning the point is here. Okay. And instead of rectangle, the polar will have the circle. For example, okay, by using the circular grid, you can easily pinpoint your coordinate in polar. Okay, so remember, we are now moving away from xy. Okay, so your perspective in xy system need to remove and change to polar system. So imagine, like, for example, you need to imagine the area, for example. Now the area, usually you integrate, right? So let me write here. Usually you integrate from A to B. Okay. A, B, usually it can be Y or X, right? Now in polar, A and B is theta. From theta this and theta this, and then you have the, like a pizza, right? The sector. It's called the sector. Okay, that's the important thing. But anyway, before we go into the calculus part, the integrations, let me introduce you how to convert. Okay, I think this is. Let me write the xy first. Y, x, and then making a triangle. This is r. Let's say this is another x here, and we have theta here, and with this theta we can project this y and this y in red with sine and cosine, right? So x is r, or y. This is wrong. X, y. R cos theta and y is r sine theta. Also, you can find the tangent. You can also find the relations between x squared plus y squared is r squared. Okay, from the Pythagorean, and then if you remember that this is also the circle. So if you moving around here, it will be the circle with these relations, right? Okay, now if you have polar 2 pi over 3, what's the Cartesian? So if you have 2 and pi over 3, remember that in polar, this is radius, this is the theta. Okay, so if you need to convert polar to Cartesian, you need to just use these 4 relations. Okay, so for example, we can write that this r is 2, this theta is pi over 3. So your x is 2 cosine pi over 3. Your y is 2 sine pi over 3, and you can directly say this is 1, this is square root of 3. So the Cartesian is 1 square root of 3. It's pretty simple. It's pretty simple if you just convert the coordinate. Okay? You can also convert the equations using uh, the same way, the same method. Okay. Another thing, what will happen if you have the polar? Let me write here some polar equations. Okay, polar equations. If you have polar equations, r equal 3, what will be the shape? What is the shape? If you have r equal 3, what is the shape? Circle, right? It's a circle. Okay. If you have a polar and it's just saying r equal 3, meaning you will have a circle. A circle with the r is 3. Okay. Or let me, for example, if this is 1, this is 2, and this is 3. Okay. what will happen if you have r, or not r, theta equal 1? What will happen if you have theta equal 1? What will be the shape? Use your imaginations. Always start from here. Let's just say theta equal 1 is like this one. Okay. So meaning theta equal 1 will be at these positions always, right? So it's like straight line. Okay. So it will be like a straight line. The shape will be straight line. Okay. Let's say this is polar axis. And let's say this is theta equal 1 here. Okay. Now, the third case, what will happen if you have r equal to cosine theta? I think I already mentioned in basic math, right? Some of you. What will be the shape if you have this polar equation? Yeah, remember? uh, anyway, you can start by try the special angle that you can imagine. Like when theta is 0, it's 1, right? And then maybe theta is pi over 4, it's square root of 2 by 2, right? Or you can draw the line. Okay, I will draw the line, but remember, okay, the line is not xy. This is just to help draw the polar equations. Okay, so this is the polar axis. Okay, let's start from theta equals 0. Theta equals 0 is cosine 0 is 1. So radius 2, right? So maybe I will write here. Maybe this is 1, 1, and then 2. So I start from here, from here. And then you need to increase the cosine. Maybe the easiest one, maybe pi over 3. It's half, right? So it's 1. So maybe here. Okay. And then so 2 is here. Maybe 1 is here. And then the pi over 2 is 0. So it's going back here. So by the end of the day, if you check all the special angle, you will have a circle. A circle to cosine theta. Now the same way, if you have 2 sine theta, okay, what will happen to sine theta? Now this is cosine, and then now sine. The difference is at the very beginning, right? Cosine theta, we start from the maximum radius here, the radius 2. Sine is 0, right? So it start from this here. So sine will be, okay, got it? What I want to show you here is we will have a pattern. Okay? 2 cos theta, 2 sine theta. What will happen if r is negative 2 cos theta? The easy way to remember the negative is we need to mirror, right? We need to mirror. So negative 2 cosine theta is on the left. Okay. What will happen if negative 2 sine? at the bottom. Okay, all this positive negative in all polar curves will occur, not only in the circle, with other forms also will occur. Okay, so that's the easy way to see the pattern and how you maybe visualize the graph when you working on some equations. Okay, that's the circle. Another curve that interesting enough for us to observe is if you have r equal 1 plus sine theta. Okay, if we try to draw this curve, we can start from 0 or start from maybe pi over 2, the easy one. Maybe pi over 2, because sine plus 1, sine pi over 2 is 1, so 1 plus 1 is 2. So pi over 2 is here, right? So maybe it's around here. Or maybe I will draw the some circle to help drawing the curve. And again, this is not xy, this is a polar system. So I will not write any xy in the axis. And this red line is to help us to draw, not the curves. So let's say this is 2. And maybe this is 1. Okay. And between 0 and pi over 2, between 0 and pi over 2, maybe we can see some theta that can be easy to calculate. Maybe sine pi over 6, maybe, right? Pi over 6 is half, so 1 plus half is 3 over 2. Maybe I will draw the angle, maybe that way. The angle is there. Maybe this pi over 6. Maybe here at the very middle. So imagine I need to connect this dot through here, or maybe next one will be pi over 3. So probably like this. Okay. And same way, it will be like this. Okay. And you will see when you reach this point, you will get this kind of curve. It's called the cardioid. Cardioid. It's like a heart. Maybe I'm not really good drawing this line, but you can check the real one googling and you can see how the cardioid will be. Okay. If you see upside down, it will be like a heart. Okay? Because it's cardio, from the cardio, the heart. The general forms for this one is called the limmason. Limmason has several forms. One of them is cardioid. It depends on this point here. It can be later. It can be looping. It can be going outside here. So it's similar to like a fruit. Okay. And this is also using the same pattern. You see it's plus sign, right? Plus sign. If you have one minus sign, it will be, okay? If you have cos, one plus cos, it will be, okay? If you have one minus cos, it's the mirror, okay? Anyway, there will be some details on how we get to how we know the pattern and how we draw. But I will attach some video to your Moodle system later. I've already done that, and you can just see for review. But for now, I will just introduce briefly what will we see in the polar curves. Okay. So first is the cardiode, the limaçon. The general form is A plus minus B sine theta, or R A plus minus B cosine theta. And the terms A over B will determine how the shape looks like. If you have A over B is 1, like this one, like 1 plus sine, it's A over B is 1, it will be cardio. If it is greater than 1, less than 1 will be different. Okay? Maybe later I will show you. Okay. Okay, let me show you the some table. Maybe I will put some table here. Let me check the table. Okay, you'll see here. It's a little bit different. It's using C. So I will write, because R is 1 plus C. So let me write here. C is B over A. If you want to make A plus minus B sine theta. Okay. So start from here. If you have C 2.5, meaning the B is greater than A. Okay, the B is greater than A. You will have the inner. We call it the limaçon with inner loop. Okay, limaçon with inner loop. Okay, and we turn down. We make it smaller. See, maybe 1.7. Okay, the loop getting small. Okay, and at the exactly 1, as we've previously done, it will be the cardio, right? And then getting smaller, we still have this, like, we call this dimpled limaçon. Okay, so it's having similar to line or curving like here, but it's like you have like a fruit, and then you punch the fruit here, right? And then getting smaller, we got um, 0.5, right? And then 0.2. It's almost getting closer to like a circle, but it's not circle. Still not. It's close to circle. We will get the circle when we have 0. Okay? Because when you have 0 here, it's just r equal 1. We have previously mentioned that if you have r equal constant, it will be a circle in polar curve, right? So this will be curve, circle, and then getting smaller, we make it negative. it will be turned to previous lemma set, but it will move toward the negative part here. Okay, and it's getting bigger here, and it's getting dimpled. It's more curvy here, and it's become the cardioid, the mirror of the wait here, the mirror of this cardioid. This is a positive one. This is negative one. Like I said before, if you have 1 plus and you change to 1 minus, it's the mirror. Okay, the mirror. So it's become a -1 here, and then um, getting bigger in negative, it will be -2. As we see, 2.5 and -2 similar, having the inner loop, but it has bigger size in the bottom. Okay. So remember the pattern, the positive, negative. You have cos, sine. Cos will be left, right. Sine will be up and down. Okay, the pattern. Another thing is um, if you have the r equal cosine 2 theta. Okay, now r cosine 2 theta, what will happen? Let me draw the two line to help drawing. So if you start from 0, it will be the maximum r, right? R is 1, right? So maybe I will make it here. So this is 1, the r, right? And then we increase the angle, and maybe using the spatial angle, pi over 3 or pi over 6, we will have some point here. And eventually we get theta equal pi over 2, right? Pi over 2. Cos pi over 2 is 0. So it will be going back here. Okay. So we can write like this. We can draw like that. And eventually, you increasing the angle, and then you will find that this is actually going here and going here and going here, going here, going here, going here, and then the last one will be going here. Okay. Before I'm explaining this and how and why, um, I forget to mention the negative. Okay. So we have done defining the r, right? This is r theta, right? This is r theta. In all theta, r will stay at it is, right? But what will happen if you have negative r? Yes, it will be the mirror of this position. So if this is the position of r here, so the negative r will be here. Okay. In this way, you can figure why we can get this curve. Okay. Okay. You need to try one by one because cos and sine both have positive and negative, right? Sometimes it's positive, sometimes it's negative, right? That's uh, how you can figure. So when you have negative, you can uh, check the mirror part. Okay. Okay. And this is called the rose curve. And again, we will see the pattern. Okay. If you have 2 theta, it will be 4. If you have 4, it will be 8. But if you have 1, it's only 1. If you have 3, it's 3. If it's 5, it's 5. Actually, if 1 is the circle, just the circle, right? And maybe I will not go into detail of that rose curve. What I want to show you is what is other polar curve beside uh, the limmason. Okay. Now you see the first is circle and spiral. We're done with the circle, sine, cosine, right? Sine is above, cosine is in the right. And when you have negative, you know you need to flip. And you have also spiral if you have r, and then a theta. Okay. Other thing is limmason with inner loop. Okay. Cardio dimpled limmason, and we call the other the almost circle one is the convex limmason. And then this part is called the rose curve. Okay. You see, if you have 2 theta, it will be 4. If you have 3, it will be 3. Okay. If you have 4 theta, it will be 8. If you have 5, it will be 5. Okay. What will be the difference with the sign? This is all cosine, right? Cos, cos, cos. The sine and cosine, the difference is in cosine, you always start from this one because cos theta, cos 0 is 1, right? If you have, if you start with sine, sine 0 is 0. So you have different starting points. So you need to a little bit flip or rotate the. So if this is cos 2 theta like this one, the sine will be, okay. Okay, get it? And also the same thing with the 3 theta. But the important here is if you have this 2 theta is even, right? Any even, like 2, 4, you need to multiply by 2. So if you have 2 theta, you have 4. But if you have the odd, like 3, it stays the same 3. Okay. I said how we can figure this pattern. You can figure it out by drawing one by one. And you can know, okay, I now have the pattern. Okay. The last one is the lemniscate. We have 2 lemniscate, the sine 2 theta, and then cos 2 theta. The full formula is r squared equal a squared sine 2 theta. And then the other one is the same, but it's cosine. And again, the same logic here, same pattern. Cosine start from here, sine start from here. So you switch or you rotate a little bit for sine. Okay. So my suggestion is easier to start with cosine because cos 0 is 1. So you can start easily from the picture. You can draw more easily. Okay. And what will we do? Okay. We already know some polar now. What will we do in calculus for polar is actually imagine like you have this and you need to find the area or you need uh, to to cut and then find that total area. For example, if you need to find just this one loop, you can find from what angle until what angle. Okay, so this angle and this angle, right? Or from 0 until here and then multiply by 2. That's also okay. That's what will we do in the calculus part. So how many time left? Okay, because I think the next one is the calculus in polar. Maybe I will just go some introduction and then we can just finish. Okay. So 10.4, so calculus in polar. This will be just the intro. Okay. Okay, let's say this is your part of circle. We call this sector. So this is actually from a circle. Yeah, let's say that's the circle. The area of the sector is half of r squared theta. Okay. And by this area of the sector, we will use this to define our, or we approach the calculus with the sector area. Okay. Okay, let's make some random graph. Maybe here. Maybe we have the polar like that randomly, and we start from theta equal alpha until theta equal beta. So this is alpha, and this is beta. So we need to evaluate this area here in between alpha and beta. Okay. What we can do to find the relation is it's the same as what we've done before. We split this into small pieces, small sector. Okay. Because now we have the approach of sector. So we divide, we split up this. So maybe like this. We split up. Okay. Now this is having some r function of phi, a function of theta. And let me write the f is a positive function and continuous. And we start from 0 until 2 pi. And we divide the sector from alpha to beta into small pieces, into small area or pieces. And if we approach this one, maybe the small pieces here, if we approach that, maybe this one, okay. This we can have some angle here, small angle. Let's say we have the delta theta. So we can approach the delta area, approach this with the sector half. The sector is half r squared theta. So half, and then function of theta squared, and then delta theta. And then with the Riemann sum, we can uh, add all the rectangles, the small rectangles. And then from what we have done before, this is true. And we call this is the integrations definitions. This is equal. This is alpha beta half squared d theta. So your area for the polar is half d theta. Okay. Okay. And how to remember the formula? Remember the sector formula. Okay. With r is function of theta. And this way, you can evaluate any polar curves, okay, for area, for each area, okay. And I will finish until here for today, okay. Okay, any questions? If not, then yeah, last finish.